Folks, I want to look at an arc length problem and a rotational problem. Just to kind of look at the contrast between them and the similarities and differences of the tools that we're going to use. So if you recall from your reading or from the video I sent out or our discussion on radians, if we have an angle measure and a radius, we can relate those to the arc length of a sector of a circle using our relationship that the arc length is going to be equal to the radius times the angle, as long as that angle is in radians. Comes from our definition of radians. If you recall, radian measure is defined by the ratio between the arc length and the radius that that angle creates. So this is just really a variation of that tool. So find the distance along the arc on the surface of the Earth, subtended by 1 minute. Subtended is just, that goes through the angle of 1 minute. Reminding you from your reading that 1 minute is a 60th of a degree. So we have 1/60th of a degree. And to use this tool, we've really got to turn that into radian measure. So we recall that there are pi radians in 180 degrees. That's going to make those degrees cancel. And we get a very small radian measure. This is a very tiny, tiny amount of arc of pi over, 60 times 180 radians. Now we should probably clean that product up a little bit. What is 18 times 6 while we're here? 8, 4, 10, and a couple of zeros. So 10,800. So pi over 10,800 radians. So a very, very tiny angle. But that very, very tiny angle, if we use that as our angle with the Earth's radius of 3,960 miles, really the reason this problem is a little bit messy is just because the numbers are so messy. If we want to know how much arc that produces, then that amount of arc produced is the radius, 3,960, multiplied by the amount of angle, pi divided by 10,800. So we could, presumably, just say it's 3,960 over 10,800 pi miles. If we wanted to just say, hey, that's a nice answer, we could reduce this fraction, and certainly should reduce this fraction. But it might be nice to just go to a decimal approximation so we can kind of have a sense of how long this is in miles and a little more natural numbers. So I'm just going to real quick here go 396 divided by 1080. Guess I'm reducing that a little bit as I do that. And then multiply that times pi. And we get a nice 1.152, I'm going to say, by round, 1.152 miles. So if you took the big, big, big Earth and took 1 minute of angle, which is a very small amount of angle, it's 1 minute of angle. Now, we're used to 1 minute being 1/60th of something, 60 minutes in an hour and all that. So it's essentially a very small fraction of a degree. It's 1/60th degrees, which is an extremely small angle. They used to use minutes and seconds a lot, especially in navigation. In radian measure, it's a super small radian value, whatever, somewhere around 1/3000th of a radian. But how much arc length is that on the surface of the Earth? Well, it's just a little more than a standard mile. And actually, this problem doesn't say so, which is kind of unfortunate. That distance, that 1.152 miles, or if you want, 1.151917306332, big irrational number. But that amount of distance is what we call a nautical mile. If you've ever heard them talk about nautical miles or just knots in navigation, particularly at sea, that is how long a nautical mile is. It's defined as 1 minute of arc on the surface of the Earth. So it's very close to an actual mile, but it is slightly different. So, we've just technically computed how many standard miles there are in a knot. So yeah, really it's not any worse in a technical sense than our other arc length problems. It's just the numbers are so nasty. But I think it really is handy to not approximate these, just carry the exact values through until you're done, and then approximate at the end. Carrying a whole bunch of decimals around really is messier in the long run. It just takes a little bit of getting used to. Now I want to compare this to a rotational problem. We'll use roughly the same tools, but the rotational problems have some extra bits to them. So bring out a rotational problem. It's on your homework. The numbers in yours might be a little different. That's good. So we have a restaurant top of a tall building in Seattle, rotates. So this thing is rotating around. How fast is it rotating? It's rotating 0.98 revolutions or rotations per 1 hour. Okay, so that's our kind of our rotational speed. It's not our angular speed. It's not our omega because it's in rotations, not in radians. So we do need to work with it a little bit. This person sits 22.3 meters from the center of the restaurant. So that gives us a radius, 22.3 meters. Great, from the center of the restaurant. Through how many radians does this person turn in 118 minutes? Okay, so to answer that, we essentially want to turn this rotational speed into an angular speed into our omega. So we got to turn the rotations into radians. So again, we'll cancel out those rotations like we did in class the other day and put in radians. So those will cancel. We know that there are 2 pi radians in 1 rotation. So if we did that, that would get us into radians per hour. But we're asked this question in minutes. So it might be nice while we're here to turn this into minutes. So I'm going to do that too. I'm going to get rid of the 1 hour and turn that into 60 minutes. You don't have to do that, but if you don't, you'd have to turn that into hours. So it would be somewhere around 1.3 hours. So you got to convert one way or the other. Part of the problem is in hours and part of the problem is in minutes. So we're going to have to convert something. So might as well do it here. Then we can actually pre-cancel a little bit. So we'll get 0.98 times pi over 30. And we're left with, after the hours cancel, radians per minute. And that's going to be our angular speed omega. Now we could say that's, we could just decide what that approximately is. But again, it might be good just to have a decimal for it. And since we've got calculators, we can. But notice I'm moving everything around without calculating until we get to the end. But that 0.98 is already a decimal, so we're just going to turn this into a decimal right away. Divided by 30 is, we should have expected somewhere around 1/10, but 0.10, I'm going to go 263 just to carry some accuracy along. So that's our angular speed in radians per minute. So if we want to know how many radians do we go through in 119 minutes, well, we go through this many per minute, so multiply that by 119, and we'll get how many radians we go through in 119 minutes. We'll go ahead and just take that, multiply by 119, and we get 12.2124 radians, which is about 2 rotations. So 1 revolution every hour. This is 120 minutes, is actually almost 2 hours, sorry. So almost 2 hours would be almost 2 revolutions, and 2 revolutions, 12.2-ish radians. That all kind of lines up. So 12.2-ish radians. Now, it asked for exact there. Well, if it wants exact, we have to stay with this pi. So we have to go 0.98 pi over 30 multiplied by 119. That's a little tough to keep exact, but we could certainly do it. Heck, you could just say that. It's that many radians. That's an exact value. The 119 divided by 30 times 0.98 isn't a very nice number. Ugh, very ugly number. So what is 119 times 0.98? 119 times 0.98. It'll be nice if I actually hit the buttons. 119 times 0.98. So 116.62 over 30 times pi. That's about as much as I would probably clean that up. That's why I hate decimals. Make everything hard. So if you want exact value, it's not going to be nice and pretty. You could also just get, take that and take that, but it's ugly. Doesn't matter. So somewhere in that vein, what does it ask for? Yeah, I'll show you what its answer looks like, what it says it wants. So you see, it's just not cleaning up terribly well. So either just the pieces that we had, multiply all that together, and I guess they're just taking this decimal, moving it over, calling that 3,000, and then reducing this a little bit to 5831 over 1,500 pi. But they'll take either of these, it looks like. Decimals. That's why decimals are trouble. So the big key there was just turning it into our formal angular speed in radian per minute so we could multiply. And a lot like the last one, most of the difficulty here is that the numbers are kind of icky decimals. Then it wanted accurate to 3 decimal places. Well, that's our 12.212, so 12.212. How far does this person go in 119 minutes? Well, 119 minutes, how far did they go? We could actually answer that question in a couple of different ways. But again, we know the angular speed. The angular speed's the 0.98 pi over 30. If we multiply that by the radius of this circle, 22.3 meters, and that's our radians per minute, that product gives us our linear speed, or how many meters per minute we will end up with. So really, I'm going to stick with the 22.3 times the 0.98 over 30 pi. That's our linear speed. I don't want to multiply any of that together. It'd be icky. But we certainly could. We'll clean it up. You guys can clean it up. But that is our meters per minute. If we want to know how far that goes in 119 minutes, well, velocity times time is distance. So that 22.3 times 0.98 divided by 30 times pi, don't forget the pi, that multiplied by 119 minutes for our time, that's going to give us distance. So to kind of follow their vein, again, I hate decimals in my fractions. So I'm going to move that over once, that over twice. That's going to give us 223 times 98 over, we moved 1, 2, 3, so 1, 2, 3. Now there's no more decimals, awesome. Times 119 times pi. So then just multiply all this together, reduce the fraction if you can. Like you can reduce that and that a little bit anyway. That's what, 49? So, and that turns into 15000. So whatever 49 times 223 times 119 over 15,000 pi meters is your exact answer. And it does say it wants that exact answer. It's what a beautiful number. 13,00313 over 15,000 pi meters. And, calculate that out for an approximation for this next answer there, where it asks for the approximation. And 272.3 meters. So 272.3 meters, if you calculate that out. So again, like the other one, the numbers here are not terribly nice and polite, but that's actually good for us. When you're out there in the world dealing with, recording real data and working with real events, they're rarely nice numbers. So these are actually very realistic values in a lot of ways. So it's actually really good practice for us. So those two problems, particularly this rotation one on top of the tall building, tend to be a little bit sticky. So hopefully you played with that, and then hopefully if you got stuck, this helps. And if there's anything else you guys need, let me know.